Good morning, everyone. Today we're going to continue our discussion of time series analysis. This will be our second to the last meeting for the term, okay? And your last case will be about time series analysis. Just to give you an idea, your last case will be using these methods, simple moving average, exponential moving average, the SES, simple exponential smoothing, and then Holt-Winter, Regression, Kalman, and Arima. So the codes are already there. Just have to replace the codes, and then you just have to, of course, analyze the differences. And you're going to use Ramsey root mean square error, mean absolute uh, mean absolute error, and the R squared in order to compare which of these methods best model your time series. Okay, the instructions will be given. I already have the outline and I'm going to post it in Canvas. Okay, so far we have looked at the nature of time series and we have used our air passengers data set. So if you haven't loaded, please make sure that it's loaded, air passengers. And then we created an object called AP to stand for air passengers. And we studied last time that the data seem to show a trend and also seasonality. Okay, and we learned that there are statistical ways in order to determine if the data is stationary. Okay, and stationary takes two forms: stationary in what class? In mean, and stationary in variance. Okay, when we say it's stationary in mean, it has no trend. There's no upward or downward motion or tendency for the data. If it's stationary in variance, we're saying that the variance of the data remains constant over time. It's not fanning out, okay, or neither is it fanning in. So time series is considered stationary if it has both constant mean and constant variance. And you can assess it visually. However, there are statistical tests that we have studied. What are those two functions that we studied last time? What are those two functions that we use in order to test if a time series is stationary? From your codes class, you can refer to your codes. What are these? Yes? ADF dot test, augmented Dickey Fuller dot test. No? However, caution class, caution, because when the data displays strong trend, ADF test is weak in that regard. Oftentimes, it might give a wrong result. So the better way is to use KPSS test. Okay, and KPSS test where the null is equal to level. Okay, this will assume that your time series does not have a trend, is a more powerful test for your time series analysis. Okay, so you need to, the last model will be ARIMA. And in order to perform an ARIMA model, you need to convert or transform your data from one that's not stationary into a stationary data. So how do we transform our data from one with a trend or one with non-constant variance to one that's stationary? How do we transform our data? Yes. Yeah. We can do log transformation. What will log transformation do? Okay. Will it treat the trend? Will it treat the trend? Will it remove the trend? Will it detrend the data? No. Okay, that's good. Not necessarily. So how do you detrend the data? What would be a good transformation for that? You get the difference. Okay, you get the difference. Uh, if you need to get the difference and the log, what should come first? What should you do first? Dorian, do you get the log first and then get the difference, or do you get the difference and then get the log? Log and then difference. Why? Why do you need to get the log first and then get the difference? All right. You need to get the log first, okay? Because once you get the log, okay, there will be no problem with getting the difference. If you get the difference first, there's a big chance that there will be negative values. So when you get the log of negative values, you'll generate NaNs, not a number. Okay, so it's first get the log and then get the difference. Okay, so that's the process. Of course, if you try to do that in your time series, you'll notice that you'll uh, you'll have a result where there are not a number. If you first do the if you first do the difference and then get the log. Okay, so the first method that we used was uh, simple moving average. This is one of the simplest method that you can use because you just get the average. This is the formula. SMA sub t is equal to 1 over k, then summation of y sub I. So you're just adding your y values, your time series, and then what will happen when you divide it by k? You're just getting the average. Okay? And we recall, class, we performed this last time. If your lag is very long, it's large, what happens? The smoothing will be greater. Okay, so you'll have a smooth out data if your lag k is large. If you have a log k which is smaller, let's say k is equal to 2, you'll notice that your forecast behaves, it will mimic your data. Okay, so uh, let's just quickly run this class. This code, SMA4, SMA12, SMA24. You notice that the function is SMA. Okay, before I do this, let's make sure that your packages are loaded. This one, our packages are forecast, T-series, TTR, KFAS, ggplot to quant mode. Let's load them, okay, to make sure that we were able to access the functions that are with these packages. For example, TTR, SMA comes from TTR. So we need to load technical trading rules first. Okay, have you loaded them, class? Feedback, please, class. Okay, thank you. All right, so let's now quickly, this is just a quick review because I want us to reach hopefully up to Kalman filter. Okay, so we have here 1, 2, 3, 4, 1, 2, 3, 4 simple moving averages. Log 4, log 12, log 24, and log 36. And we have here another one, log 2. Okay, let me just run 4, 12, 24, and 36. So we gave it different colors so that we can see which one belong to SMA4, etc. Okay, so you can see that this is, the red one is SMA4. Okay, compared to SMA36, okay, you notice that SMA36 shows a very smooth out forecast. Right, class? Can you kindly confirm if you are able to see the distinction between a lower lag simple moving average, class? This is 4, okay? That's 4. And in fact, if we use 2 here, SMA2, where the lag is equal to 2, we can see that your simple moving average almost mimics your time series. Our time series is AP. There you go. Okay? Any questions, class? I hope this is clear, no? Pag simple moving average, the lower the lag, okay, the more close you are to the behavior of your time series. Okay? Okay. All right, so this one now, okay, this code calculates the Ramsey root mean square error for each of the SMAs. So you have here 2, 4, 6, 12, 24, and 36. Now take note that SMA2, SMA4, SMA12, SMA 36 will have different number of observations. Which will have, among these, which will have the smallest number of observations? Which one, class? SMA2, SMA 36, SMA 12, SMA 24. Which one will have the lowest number of observations? Class, please. Class. Which one? How do you get, class, SMA 36? You get the first 36 observations, average it, class. Okay. And your first data, your first prediction will be on what? Observation 36. Therefore, how many observations were removed from your forecast? 35. Right? Do you follow, class? For SMA2, since you're just averaging the first two, then you'll just be reduced by 1. SMA4, you'll be reduced by how many? 3. Okay. Pakisagot naman, class, no? Kindly, please. All right. So which of these, class? Which of these SMAs, simple moving average, will have the shortest data set, shortest number of observations? SMA, huh? SMA what? Yes? Huh? Bakit 2? Why 2? Di ba pag 36, class, you're removing 35 observations, right? Tingnan nyo. Take a look at your plot, class, here. I'm asking for the observations, number of observations, the object that you create. This is SMA 36, class. Take a look. The violet ones are your observations for SMA 36, right? You are removing 35 observations from it. Why? Because you have to get the first 36 observations, average that, add all of those, and then divide it by 36, right? So SMA 36 will have less observations than SMA2. SMA2 will have more observations than SMA12. Okay, you follow that, class? Hello, class. Thank you. Please feedback na lang para alam ko kung I know if I'm going to continue or explain more. All right. Okay, so in this code that I shared with you, notice that we're computing for the Ramsey, root mean square error. How do you compute for the Ramsey, class? What's the formula for Ramsey? Ramsey is your actual value minus your predicted value. Then what do you do with that? That's your error term. What do you do with that, class? Root mean square error. So you compute for the error, and then what do you do with it, class? You square it, right? So how do you compute for the error? Actual value minus predicted value. That's your error, and then you square it. So that's your SE, squared error. And then your M, what's your M? Mean, okay? So you have your residual squared, and then you add all of them and get the average, and then what do you do after that? R, class, R, what's R? Root, you get the square root, class. Okay, so very simple operation. Actual value minus predicted value, square it, okay? So you have several error terms, squared error terms, and then you get what? You get the mean of that, average of that, okay? Can you get the average of that? Will it be positive, class? Will the average be positive? Yes, why? Why will it be positive? Because your error squared will always be positive, right? Your squared error will be positive, so you get the average of that, it will be positive. So can you get the square root of that? Yes, so that's possible. RM as E. And then the lower the Ramsey class among the different models, the better or the poorer? Better. The lower the Ramsey, the better is the model. All right. Now, if we run this class, we ran this last time, but quickly, let's just have a very quick review. Okay. This code here will churn out missing values. Why? Because SMA2 and SMA4 and SMA12, SMA24, SMA36 will have different observations. Diba? Magkakaiba sila. They're different. SMA2 will have more observations than SMA4, more than SMA12, more than SMA24. Okay, are you following, class? Okay, good. All right, then in this next code, what I did was to remove the trim. Remove the, here class, actual trim. Okay, we removed those that are, we made SMA2, SMA4, SMA12, the same number of observations. Okay, so which will be followed? How many observations? Will SMA2 or SMA4 be followed, or SMA36? Class. Which will be followed? SMA2, SMA4, SMA12, SMA24, SMA36. The answer is SMA36, right? Right, class? Because you are making it in such a way that all of them have values, right? So SMA36 is shorter. It has less values than SMA2. So what we're going to do is to remove those values that SMA2 has. Okay, we're making the number of observations the same. Okay, so when we run this class, when we run this, notice now that there are no more missing values. We trim this. Okay, there you go, class. Unlike in the previous one, here, okay, shorter object, okay. SMA2 is longer object, okay, etc. For this one, okay. And based on the Ramsey, which is the best model class among these, SMA2, 4, 6, 12, 24, 36, which is the better or the best model? SMA2, of course. Naturally, class, when we plotted SMA2, it was really very close to the original data set, right? Compared to SMA36. Okay? All right. Now, a practical use of SMA we discussed last time is that this can be used in trading. Okay? So what's oftentimes used as an indicator whether to buy or to sell your stock. Okay, so this is not just something that's conceptual. This can be used. This is used by technicians in trading their stocks. So they oftentimes use SMA 50 and SMA 200. Okay, so which is more smooth, SMA 50 or SMA 200? Which is more smooth, class? SMA 50 or SMA 200? SMA, of course, 200, because we said that the larger the lag, the more smooth your SMA will be. Okay, so SMA 50 will be the shorter here, and SMA 200 will be the longer lag. And we said that if we plot this, class, if we compare the plot of SMA 50 and SMA 200 using Apple, here we're using Apple stocks. Okay, so we have this plot, class. So this is, okay. How do you know if it's SMA 50? Just by looking at the plot, class, how do you know it's SMA 50? Sorry? Konti? Or it starts ahead, no? Here, the red one, class. This is SMA 50, right? Remember, class, if it's SMA 50, you just get the average of the first 50 observations. So your plot will start on the 50th observation. While SMA 200, okay, this one green, it will start on the 200th day. All right. So how is this used in stock trading? Okay. These are indicators or these are signals. When the red the SMA 50 crosses the SMA 200, goes down below the SMA 200, this is what signal is this? It's a sell signal. Okay. And when the red one, okay, this one, when this crosses the red one, the SMA 50 crosses your green uh, SMA 200, then that's a buy signal. So buy, sell, buy, sell. So this is an example of how simple moving average is used in trading. All right. So the next, my apologies class for going through this quickly because this is just a review. The next thing that we studied was exponential moving average, EMA. Okay. And it's the same thing. Okay. The only difference between your EMA and your SMA, if you recall, what's the difference? SMA, EMA. Okay, the difference is that for SMA, simple moving average, you're weighing your past values equally, 1/k. So equal yung weight nila. It's just average. On the other hand, for exponential moving average, okay, we can assign the weight. And usually, the larger weight is given to the more recent figures. So for example, if it's EMA 36, then the figures, the earlier figures will have lower weight as compared to the later figures. Okay, so we ran this last time. Okay, let's see how the plot looks like. We're plotting EMA 6, EMA 12, and EMA 24. Sorry. Okay. Why doesn't it plot? The blue, the red, the green. Or is it plotted? Maybe I just can't see it. No, it's just blue, no? Okay, so did I change this? Okay. There's supposed to be 6, 12, and 24. Okay, let me rerun this. Okay, I'm having problem with did it run in your case, class? Because I think I accidentally changed some of my codes. How about in your case? Let me see this one. Not here. Okay, anyway, I'll just check this first. Okay. There's supposed to be a plot for EMA 6-month, 12-month, and 24-month. And without looking at the plot class, let's guess which of the EMA here, 6, 12, and 24, will be very close to your original data. Is it EMA 6, EMA 12, or EMA 24? EMA 6. It will be very closer to your data, actual data, as compared to EMA 24. All right. All right. So here, we're also, let's compute for the Ramsey later on. EMA is also used for technical trading. Same thing as SMA. For SMA, we normally use SMA 50 and SMA 200. For EMA, we use EMA 12 and EMA 26. So if I plot here 12 and 26, so we're using Tesla here, Tesla stocks. So this is 12 and 26. Okay, what's the green one, class? What's the green one? Is it 12 or 26? The green one here. 12 or 26? It's 26. Why? Later siya, no? It's later. EMA, the red one is EMA 12, of course, because you average the first 12 observations. For the green one, EMA 26, it should come later because you're averaging the first 12, 26 observations. So similarly, you take a look at crossovers. Okay, when the red one crosses over your green one downwards, okay, that's a sell signal. When the red, again, as EMA, the red one, 12, when EMA 12 crosses over or goes higher than your EMA 26, then it's a buy signal. Okay. All right. I didn't get to see the video class which I posted. Did we start doing exponential smoothing last time? Did we, class? Exponential smoothing? No? Okay. So what's the difference between SMA, EMA, and exponential smoothing? What's the difference between them? Exponential smoothing is quite similar to EMA because what happens here is that you give greater weight to your most recent values and lower weight to your more your values that are further from the current value. Okay, so we're going to discuss three types of exponential smoothing. You have SES, simple exponential smoothing. You also have Holt's linear trend, and you have your Holt-Winter seasonal model. All of these class are here in your notes, and there are explanations for this, so you won't get lost in your case. So the formula for exponential smoothing is this one. Okay, so you have here your alpha, okay, and 1 minus alpha. You notice that your predicted value, your y sub t, is equal to, it's equal to what, class? What's y sub t minus 1? So take a look at the formula. Y hat sub t, what does the y hat there signify? Is your, if you see the hat, class, it means it's your plus, sorry, forecasted value or predicted value. Then this one, y sub t minus 1, what's this? Previous, yeah? Previous what? Previous actual value or predicted value? Actual value. And then y hat t minus 1 should be your previous predicted value. So your predicted value at time t is equal to your previous actual value times a certain smoothing constant plus 1 minus the smoothing constant times your predicted value, previous predicted value. Okay, so we will not get into the nitty-gritty details of computing. So we'll just go here. So I have here some notes, class. Okay, notes about your SES. SES is your simple exponential smoothing. Okay, All right, let's plot this. So we're creating your SES model. Okay, and your SES is equal to SES, that's the function. This is our data. And then H is equal to 12. That's your lag. Did I show the formula here? Okay. All right, so if you run this, so we're now creating here an object called fitted time series. This is your forecast, and we're converting it into a time series. Then the start date is equal to the start of AP, and then the frequency is the frequency of our data AP. Okay, the frequency of our data is 12, so this is monthly data. And then we're going to plot this. Okay, so let's run this. Okay, and then what do we see here? We're plotting both the, okay, if you take a look at our code, ggplot plus we're plotting the line for AP. This is the actual value, and it's colored red. And then we're also plotting the forecasted value, and it's colored blue. Okay, so this is now your exponential smoothing there. So what do you notice about the exponential smoothing class? The black one is your actual value. The blue one is your predicted value. Does it look similar to the forecast of moving average or simple moving average or exponential moving average class? It's also able to mimic your data, right? It's also able to uh, follow your data. Okay, any questions about this class? Okay, no questions? Okay, this is the forecast class. Okay, all right. So this one class, these are plots. What's alpha class? I don't have my pen with me. What's alpha? Alpha is your smoothing constant. Remember that your predicted value y sub t, okay, let me flash it again. Your predicted value y sub t is equal to this one, right? Alpha times your past actual value plus 1 minus alpha times past predicted value. So your prediction will vary on your alpha. Okay? So if it can be 50-50 or your alpha can be a measure of proportion ranging from 0 to 1. Okay, if your alpha is 1, what does that mean, class? If your alpha is 1, then your predicted value is simply equal to your previous actual value. Did you get that, class? Alpha is equal to 1, alpha is equal to 100% will mean that your predicted value at time t will be equal to what? That's 1 times y sub t minus 1. This becomes 1 minus 1. This becomes 0. Right? What do you call that, class? Our prediction for today will be equal to the value yesterday. There's a term for that. What do you call that term, class? Does anyone know that, class? Okay, I'd like to predict the sales for today. What will be my prediction? What was the sales yesterday? 100. So my prediction for today is 100 because the sales yesterday was 100. because we're using alpha is equal to 100%. In other words, 100% of the weight of your predicted value will go to the previous value. Kasi it's only a proportion, alpha and 1 minus alpha. Okay? So if alpha is equal to 1, then this becomes what? What kind of forecast is this? It's called your naive forecast. Naive forecast in the sense that let's not create any model. Let's just use the past value. Okay, what was the value yesterday? 100. That's our forecast. Right, Cass? Your y sub t, your forecast now is equal to alpha. What's our alpha? If you were using 1, so this is 1 times y sub t minus 1. Okay, what's our y sub t minus 1? That's the actual value yesterday. So we can use that. We can use the value yesterday. Okay, so for tomorrow, what will be our forecasted value? For tomorrow, what will be my forecasted value? Okay, whatever the sales I had today, okay, that will be my forecast for tomorrow, because it's always the past value. Okay. Right, so here are examples, class, of different alphas. Okay, alpha 0.2, alpha 0.5, alpha 0.8, and it shows to us the differences between your forecasts based on the different alphas. Alpha of 0.2 means you're giving 20% weight to your actual value yesterday, and 80% to your forecasted value yesterday. So that's what this means, class. Okay, and if I plot this, okay, so this is 0.2, this is 0.5, and this is 0.8. What do you notice, class, about our forecast? You get what are those blue lines? Those blue lines are your predictions, those are your forecast. So if you're giving more weight, an alpha of 0.2, class, means you're giving more weight to what? Predicted. The formula is y hat sub t is equal to alpha times y sub t minus 1 plus 1 minus alpha times y sub t minus 1 predicted. So you're correct. You're giving more weight to your predicted value. How many percent? 0.8, right? 0.2 will be the weight for your previous actual value. 0.8 will be your weight for your predicted value. If it's 0.5, then it's the same. If it's 0.8, then you're giving more weight to your actual value. So you can see here the differences. Okay, which is a longer range, class, which is a longer confidence interval for your prediction, which has a longer confidence interval. If you're giving more weight to your previous values, 0.8 kasi, class, di ba? 0.8, right? Which is this one. Alpha is equal to 0.8, which means you're giving 80% of your weight to your previous values, your y sub t minus 1, and then only 0.2 to your predicted value, y hat sub t minus 1. Okay, and the difference in the plots is that, okay, this is 0.2, this is 0.5, and this is 0.8. So giving more weight to your actual value will result into a forecast that has a higher confidence interval, mas malawak, class. It's wider compared to giving more weight to your past values. Okay? All right, so I put here some notes, class. Okay? So for example, the larger alpha, the model responds more to recent data because the weight on the most recent data is much higher. It is more reactive. So if alpha is it's larger than your 1 minus alpha, it is more reactive because you're putting more weight to your actual values. So that's why it will have a larger confidence interval as compared to 1 with alpha that's lower. Okay? So that's why I said here, when your alpha is bigger, okay, let's say more than 0.5, your forecast will be more volatile. It will be quicker to respond to changes. Okay. However, it can overreact to short-term noise. Okay. Lower alphas, on the other hand, is more, let's say, quote unquote, tame. Okay. All right. So if I plot this, so we're just plotting here, class, the okay. So what do you notice here, class? What is the red one there? What is the red one? Alpha 0.8 or 0.2? Which is more reactive, class? Which reacts more as your data moves, as your data fluctuates, your forecast fluctuates also. Which is more reactive? The red one or the blue one, class? Which is more reactive? Blue? Blue ba, class? Blue, right. It mimics more your data. It reacts more. So since it's more reactive, what's the alpha there? Is it higher or smaller? Higher. So alpha 0.8 there is your blue. Correct? Because your alpha is the weight you give to your previous values, class, actual values. Okay, so that's what I meant a while ago. So a higher alpha compared to 1 minus alpha will be more reactive because you're giving more weight to your actual value, and your actual value captures the quick changes. Okay, let's now compute, class. Of course, for this one, who do you think will have a lower Ramsey? Who do you think, class, will have a better Ramsey? Is it alpha is equal to 0.2 or alpha is equal to 0.8? Better Ramsey, class. Class, better Ramsey. So the model, class, that follows more your original data will have the better Ramsey because it follows your original data. Okay. So when we compared a while ago, which follows more your data, is it an alpha of 0.2 or alpha of 0.8? 0.8. Therefore, the Ramsey of alpha 0.8 will be lower. Okay, as expected. If we run this, so we are okay. Let's see. What is the Ramsey for alpha is equal to 0.2 and alpha is equal to 0.8? It's now computing for the root mean square, and as expected, class, the root mean square error for your alpha, your smoothing coefficient, which is higher, will be lower. Okay, any questions about this, class? Any questions? Any questions? All right, so let me just summarize, class. Simple exponential smoothing follows the formula. Your forecast y hat sub t is equal to y sub t minus 1 times alpha times y hat t minus 1 times 1 minus alpha. So you're using both the past predicted value y hat sub t minus 1 and your past current past actual value y sub t. Okay, your alpha is multiplied with your past actual value. So if you put a greater weight to your alpha, okay, then that means that your model, your predictions will be more reactive to changes in your actual data, and your Ramsey will be lower. Okay, all right, let's pause. Okay, so one weakness of the simple exponential smoothing is that it is quite weak in modeling our time series with trend. Okay, so this formula, the simple exponential smoothing, where's that? Here. Okay, exponential smoothing, simple. It's quite weak when there's trend. So a an improvement was suggested, okay, to the simple smoothing average, simple exponential smoothing, the SES, and we call it the Holt's method. Okay, so this one class. Here, improvement of the simple exponential smoothing, we have the Holt's linear trend model. So the Holt's linear trend model is able to capture trends. Okay, so let's run this. We're creating this object called Holt model, and the function is Holt. So we're modeling AP. AP is airline passengers, and then we're predicting the next 12 values. Okay, so from the Holt model, we create fitted values. We use fitted, okay, and then we convert it into time series, okay, so that we can plot it here. So that's how this code actually runs. So we create the Holt model, okay, using the Holt function for our data AP, 12 predictions in the next 12 months. And then we create a fitted value, the predicted values using the fitted function, okay? And then we convert our fitted value into a time series so that we can plot it. And then we plot it here. So here we're plotting both AP, okay, and our fitted value. So let's run this and see how your Holt method fares. Okay, take a look at this class. All right, so it's quite a bit similar to our simple exponential smoothing. Okay, the reason could be because we have only 144 observations, so it's quite a small observation. However, let's say the advantage of Holt method over the SES becomes apparent if we have a larger data set. Okay, but let's see how it compares. Okay, so let's compute for, okay, we'll compute for the Ramsey later. And this one class, the third improvement, okay, so we have simple exponential smoothing, then we improve it using Holt method, and then another improvement is Holt-Winter's model. Okay, the Holt-Winter's model is best if you have not only trend but seasonality. Okay, so simple exponential smoothing is okay, but it might be not be able to capture if your data has trend and seasonality, which our AP has. Okay, the Holt method, which is an improvement of the seasonal, simple exponential smoothing fare better if there's a trend, and the Holt-Winter fare better when there's seasonality and trend. So same thing, here we're creating the Holt-Winter model, which we're using HW. Then we predict, okay, the 12 observations. Then we convert it into time series, and then we plot it also. So this is quite similar to the code above, where we created the Holt model, and then we predicted, and then we converted into time series, this one, TS, time series, and then we plotted it. So let's see how Holt-Winter's fare. So we're plotting it, class. Okay, now take a look here. So this is our model, right? The red one. And as you can see, it's except for the first few values, the later values are more closer than the SES and the Holt method. Pause for a while, class. Are you still with me? Okay. And then take a look at the forecast, class. Look. Take a look at the forecast of your Holt-Winter. Okay. It's more precise. Okay. It was able to follow really even to the forecast. For SES, it was more broad. Okay. The Holt-Winter was able to, the blue one here is your forecast. And as you can see, it was able to really mimic even the past values. So that's the power of Holt-Winter. Okay. And we can see here, let's compute, class. Let's now compare the Ramsey, root mean square error of SES, of Holt, and then your HW. HW is your Holt-Winter. Mr. Kaampwed, what's your Ramsey for SES, Holt, and Holt-Winter? What's the values, class? Can you run that, please? Which has the lower Ramsey? What's the Ramsey for SES? How much? 33. Okay. Ramsey for Holt. Which is higher, SES or Holt? Okay, SES is higher, class, compared to Holt. How about Holt-Winter? 17. Okay, so you can see how much lower Holt-Winter model is compared to a simple exponential smoothing or the Holt method. And that's because Holt-Winter is equipped to handle both trend and seasonality. Holt can only handle trend, but not so much seasonality. SES can handle not so much trend and seasonality. So these three exponential smoothing methods, we were able to show that the more powerful one, class, is your Holt-Winter method. As you can see here, the Ramsey for Holt-Winter is just 17. For SES, it's 33.59. For Holt method, it's 33.53. Okay. And this results, of course, class, I expect in your case, because you're going to use this in your final case. Okay, so for this one, okay, this is also an application of exponential smoothing in finance. So we're using here Tesla data, and okay, we're just using here okay, let's run this first. This time I'm using tidyquant in order to get Tesla data, because all along we have been using quant mode. There are other packages that can download data. So here, tidyquant, let's run this. Of course, you can make this as Pacman, please, if you don't have tidyquant yet. I'll give you time to load tidyquant, which has almost the same capabilities as quant mode. And then the function here is TQ tidyquant get. It's not get symbols. So that's the difference. Okay, so let's get Tesla data. So this is your Tesla. Okay, let me pause for a while and see if you're able to follow along. Okay, you got the plot of Tesla. Of course, you could have used quant mode for this. I just introduced another one just for you to be aware that, but you can use tidyquant. Tidyquant is also powerful. It has the similar features as get symbols. Only that tidyquant comes from the family of packages ggplot2. It comes from the tidyverse, the universe of tidyverse. So in that regard, it's more powerful than quant mode. Okay. All right. So again, this is just an application class of simple exponential smoothing. Okay. What are we plotting here? We're plotting Tesla data. And what do you see, class? You see how close your SES is to your actual data, right, class? And why is it able to do that, class? Because Tesla data has it doesn't seem to have a trend. It doesn't seem to have seasonality. So if your data is like that, then SES will suffice. Okay, there was no need to do Holt's method here, neither Holt-Winters. Okay, but of course we could have used that and perhaps compared, which would have given us the lower Ramsey. If we use SES or Holt method or Holt-Winter. Okay, I leave that to you as an exercise class. But as I said, SES is the simple exponential smoothing worked here perfectly because it did not have trend and seasonality. If your data is like that, then SES is powerful enough. Okay, then so we have done simple moving average, exponential moving average, simple exponential smoothing, Holt method, Holt-Winter method. The sixth method, class, is your regression. Okay, regression with seasonality. Okay, so you can use regression to predict your data AP. All right, so what are we doing here? I hope that you should be able to understand this. We're creating an object called DF, and it's a data frame, okay, where your y-axis is the numeric value of AP. Your time is equal to the time in your AP object, and then your month is equal to factor cycle of AP. Okay, let's run this first. Let's run our DF, control enter. And how does our DF object look like? So it's here. Okay, so what do we have here? What are our variables here? You have your y, that's your value of your AP, then time, okay? Now why is the time like this, class? Time and then 1.0, 1.16. What's that, class? Can you guess, class? Why is our time like that? And then our month. How many months does AP have, the AP object have? your month class is a cycle class, right? 1 to 12, and then 1 to 12, and then 1 to 12. So 1 is your January, 2 is your February, 3 is your March, etc. How about the time class? 1, 1.08, 1.16. What's that? Can anyone guess, class? It starts with 1 time, and then 1.08. What's that? Guess, class? And notice it's constant. It's constant, class. What's that? That's sure. The distance between each month, class, it's constant. Okay, and it's very easy to prove. What is that 0.08? It's a distance between your months. Okay, anyway, well, that's not important to us now. What's important for us is this one. So, do you recall this, class? Do you recall this? Model LM, what's that? What's LM, class? Should be very familiar with that now, right? LM, that's your linear model. What's our dependent variable? Our data, Y, right? Regressed on time plus month, okay? And our data is equal to DF. Okay, then we summarize it. See, model LM summary. Error, where's that? In plotting, no? Okay, error in plotting. Let's see the result first. Plus, now this is your regression output here. So this is our regression output. I run summary first. Okay. So this is our regression output. You have here your time, okay, and it's statistically significant. And you have here Y month 2, class. What happened here, class, in this regression output? What happened here? This is our data. What happened here in your regression output for time, for month, class? What happened? Sa regression output natin, month was treated as a what? Month was treated as a, you should know, class, by the result here. Take a look. Month 2. What happened to month 1? What happened to month 1? It became a benchmark, class. Okay? Month was treated as a what? As a factor. Okay? And what does this mean, class? Negative 9.41. What does that mean? That month 2, okay, is what? On the average, the values of month 2 is less than 9.41, okay, passengers compared to month 1. Okay. Diba, class? Remember, these are factors. Month 3 on the average has 23 million yata to million passengers more than month 1. Month 7 has 93 million passengers more than month 1. Month 11 has 35 million passengers less than month 1. Recall that these are benchmark references. Okay, so that's what they mean. Okay. And let me just, I think I made another one. The second one, class, I think I corrected the first one for the plot. Okay, so for the regression, class, I here. Here is our regression model class. Here. There. Okay. And I will not anymore discuss so much the interpretation of this because we have had more than half the term about regression. All right. So let me go here, class. Let me just, okay, it's almost time, although we have some more minutes left, but I think I'll end in comparing these models. I leave you, class, to, okay, please study this. Kindly take a look at this. This will be our last. Kalman filter and ARIMA will be our last methods. Okay, and you need to know this because this is part of your case. All right, so let's just run this last one, class. Let's load forecast T-series. I think metrics, this will be the first time for us to load this. Kindly load this. So actually this one, we don't need this anymore. I'll delete this because we loaded it here already. Okay. So for this last one, class, it's still same data, AP, still have that. Now, what's happening here? We would like to compare the different models, class. We'd like to compare simple moving average, exponential moving average, simple exponential smoothing, Holt-Winter, and the regression, the 6 models. Now, what we're going to do is we're going to create a train and test. So what's the difference between this? Your train data will be what we're going to model, and our test data will be what we're going to subject the model that we create in train to testing. Okay, so I have here already the function for simple moving average. Okay. And for the 5 functions class, for the 5 methods, I already have it here. So, and then here, I created a function for calculating metrics. We'll calculate Ramsey, MAV, mean absolute error, and R squared. And then we're going to print, okay? We're going to calculate, and then we're going to print and differentiate SMA, EMA, SES, Holt-Winters, and linear regression. So this code is doing that, class. So if I run this, so let's just run this last code here. All right, take a look at that, class. So of these 6 methods, which fare best as far as Ramsey is concerned? As far as root mean square error is concerned, which was the best model, class? Holt-Winters, right? It has the lowest root mean square error. How about in terms of MAE? MAE, class, mean absolute error. Which one? Holt-Winter pa rin, no? Lowest mean absolute error. How about R squared, class? In fact, the other 4 methods have a problem, negative R squared. Negative R squared is a bad thing with regression. Okay, it means that our data is not even able to compare with just using the average. Okay, that's what that negative R squared means. No? And the best in terms of R squared is still your Holt-Winters. Okay, so you can see how it even outperforms your linear regression, your LM function. So in this regard, it's best if we're going to forecast AP class, it would have been best to use Holt-Winters based on better Ramsey, MAE, and R squared. All right. So I leave you class to please read yung Kalman filter kasi that would be our last discussion plus the ARIMA. Okay. So now on Thursday class, we most probably class we will be in Bangkok to present a paper. So I don't know if I will be able to meet you exactly at 11 o'clock, but definitely I'll give you the discussion of Kalman filter and ARIMA. Okay, so you in case where we push to, because I don't know yet with the condition in Bangkok now because of the earthquake. Okay, so if we're not able to push through, then we meet online. Otherwise, class, I give you the video on that. Okay, so thank you so much, class. I